the title's a bit unfortunate only because it's part of a kind of a larger project. And I didn't realize, it's easy to say you're going to do everything you need to do in order to kind of establish a positive view. But, as I realized, 45 minutes is not that long, so I'm only able to do a little piece of it. But ultimately, just kind of like an autobiographical note, I was kind of, I'm as I expressed in Job's talk, I'm obsessed with trying to explain the differences in symmetry by appealing to, the internal structure of completions. I was happy for a while to do that with positionalism until, until Maureen Donnelly's paper, Positionalism Revisited, came along, and she kind of showed me that you can do this with, you can handle relations of any fixed arity relation with any symmetry, including cyclic symmetries. And so once I saw somebody kind of do that, do both those things at once, I really wanted to, it caused me to kind of rethink things. And so what I'm going to do now is effectively try to resurrect the standard view a bit. And of course, there's going to be issues that I'm not going to get to, standard objections to the standard view. I've got some things to say about them, but feel free to push me on them in Q&A or on anything else. So I'm going to do just two things today. I want to show that the standard view can handle any fixed arity relation with any symmetry such a relation can have by using techniques that Donnelly employs to develop her view. And then I want to basically just run one argument, an argument to prefer this, this standard view so understood over Donnelly's view. I think it has, from a metaphysical, formally they kind of work the same way, but from a metaphysical perspective, I think that the standard view has some advantages. In particular, I want to show that the standard view doesn't, like relative positionalism, posit relative properties where there should be none. And I'm going to do this by kind of applying some lessons learned from Jack Spencer's 2016 investigation into the phenomenon of relativity. And I'll talk about what relative properties are and what relativity is as a phenomenon later on. Unfortunately, because the formal aspects of Donnelly's view are so complex, after just briefly introducing the standard view, a big part of the time is probably going to be devoted to explicating her view, relative positionalism, and then the transference of it to the standard view is relatively straightforward. And that's not to say that, I suggested, well, yeah. So then, so I'll just show, so I'll just do that in section 2. I'll make that transference. And then in section 3, I'll give my little argument for the standard view, kind of understood now as being able to apply to every fixed arity relation. How it does a little bit of a better job than relative positionalism. So the standard view, as it's usually introduced, is usually discussed in terms of binary relations only. And that's not to say that no one ever, no one hasn't thought, yeah, it can be generalized. Just as an example, I think in Fraser McBride's 2014 paper, he kind of alludes to the idea that a completely non-symmetric ternary relation is going to have 5 converses, and that's going to kind of fall out on the view that I'm talking about. So in a way, I just kind of want to develop it and show exactly how the methods that Donnelly uses by invoking group theory can allow us to do it with the standard view as well. So the standard view, as it's usually introduced, and this is pretty much just paraphrasing from Russell, every relation is going to have a direction or a sense. Another way to think about it is that it's going to apply to its relata in an order or proceeding from one to the other. Secondly, every relation is going to have a converse, which applies in the opposite order to that in which R applies whenever R applies. And then the difference between a symmetric relation and a non-symmetric relation is that the former is identical to its converse while the latter is not. SV2 and SV3 are going to have to be modified just a little bit in order to generalize, but I'll get to that at that time. So let's talk about relative positionalism first. So roughly the view is that when some things stand in a relation, they do so by being assigned to certain positions of the relation relative to one another. And that sounds weird when you first see it, but on Donnelly's view, positions are understood not as holes or slots in a relation that its relata occupy, but instead positions are understood as unary properties that its relata instantiate relative to one another. So an example of a relative property is going to be something like, well, it's just going to be anything that can be in, that something can instantiate only relative to something. So, a possible example of a relative property is, if you think it's a property, the property of being north, in kind of relative property talk, you could say that SFO is north relative to LAX. And so we'll come back to these relative properties later. There's an advantage of her view over a kind of absolute positionalist views, as she calls them, views that think of positions as slots, is that her view can handle any fixed arity relation, regardless of its symmetry, even if it's cyclic, and give correct answers about the numbers of ways it can apply to M objects for any M less than or equal to N, where N is the arity of the relation. A couple of more details. The number of relative properties that a relation has and the ways that they can be instantiated is going to be indicated by the relation's adicity or arity, I'll use those terms interchangeably, and its symmetry structure. And Donnelly's going to analyze its symmetry structure group theoretically. And this is going to kind of be kind of what helps us figure out, well, yeah, this is going to kind of co-vary with the number of ways that the n-adic relation can apply to M objects. One complication is that in the case of ternary relations and relations of higher arities, the relative properties that Donnelly has to invoke are instantiated by something not just relative to one thing, but relative to a thing, and so on. For however many, for whatever n is the arity of the relation, or the relation at issue. So an example of this kind of relative property, just to give you some kind of intuitive handle about what sort of things she might have in mind when she appeals to such relative properties, is something like, maybe if you think that closeness is a relative property, you could say that SFO is close relative to PDX, the Portland airport, relative to the LAX airport, right? And that's just a fancy relative property way of saying that SFO is closer to Portland than it is to, from the perspective of someone at LAX, San Francisco is close as compared to Portland, right? So she has kind of a couple of theses that she requires to kind of state her view. The first I call her Base Thesis. And this is the idea that every n-ary relation has between 1 and n factorial relative properties, each of which is instantiated by something relative to anything else, only if that thing stands in R. And when some things x1 through xn instantiate R, a couple of things hold. First of all, each of R's relative properties is instantiated by one of x1 through xn relative to another, and so on, relative to the remaining one. And secondly, every ordering of x1 through xn is such that at least one of R's relative properties is instantiated by the first relative to the second, and so on up to the nth, relative to the nth. So Loving, for example, and I'm going to indicate arities with just a little superscript. Loving has between 1 and 2 relative properties according to the Base Thesis. And we also know that if Goethe and Buff stand in the Loving relation, then first of all, each of its relative properties is instantiated by one of Goethe and Buff relative to the other. And we also know that at least one of its relative properties is instantiated by Goethe relative to Buff, and at least one is instantiated by Buff relative to Goethe. And that's all we know so far from the Base Thesis. She'll say something else to help us distinguish between relations of different symmetries. But in order to do that, we need to talk a little bit about group theory. Relations are going to have different symmetry groups. And a group is just a set of entities which is closed under a binary associative operation which I have just abbreviated by dot, and which includes an identity element and inverses for that operation. So another way of saying all that is just that that operation is going to be closed on the set. It's going to be associative. There's going to be an identity element, which no matter how you apply it with the operation, it gives you the, with one of the elements of the set, you get that same element back. And then you have inverses. And one thing's an inverse of another if when you apply them together with the operation, you get the identity element. So I'll give a couple of examples. A symmetry group is going to be a group of permutations. So let brackets around x1, x2, xn, and so on, xn, denote the function that is a permutation of 1, 2, of the set 1, 2, up to n, that maps 1 to x1, 2 to x2, and so on, up until mapping n to xn. So for any permutation group, S sub n, where n is the number of permutations in that group, its group operation is going to be function composition, which I have abbreviated by the little circle here, where the composite of these two permutations is the permutation that maps each I in the set 1 through n to the result of applying q to I and then p to the result of that. So for example, if you consider the permutation group S2, which just contains these two permutations, namely the permutation that maps 1 to itself and 2 to itself, and then the permutation that maps 1 to 2 and 2 to 1, composing the permutation 2, 1 with the permutation 1, 2 gives you the permutation 2, 1, because applying this thing, which ends up being this thing, applying the identity permutation to 1 is of course going to give you 1, and then applying the permutation that takes 1 to 2 and 2 to 1 is going to give you 2. And similarly, in this case, when you apply the whole thing to 2, you're applying the identity permutation to 2, which gives you 2, and then applying the kind of the permutation that maps 1 to 2 and 2 to 1 to 2 is going to yield 1. So that's kind of how you should think about kind of doing these function compositions if you're not familiar with doing them. The group identity element in a permutation group is going to be the permutation that just takes 1 to 1 and 2 to 2 and so on if there's more in it. And you can do the calculations and show that composing the permutation that sends 1 to 1 and 2 to 2 with itself just gives you that same permutation. And you can also show that composing the permutation that maps 1 to 1 and 2 to 2 to the one that maps 1 to 2 and 2 to 1 is going to yield that same one that maps 1 to 2 and 2 to 1. And then inverse elements in these permutation groups are just going to be inverse permutations. So the inverse permutation of the identity element is just going to be itself, because when you compose it with itself, you get itself, you get it. And then the identity permutation of the permutation that maps 1 to 2 and 2 to 1 is going to be itself, because when you compose it, you get the identity permutation. And in some larger symmetry groups that have more than 2 members, like S2, you know, it won't always be that something is its own inverse. That's kind of a special fact about S2, but anyway. So hopefully that crash course in group theory was at least semi-catchable. So a relation symmetry group is going to be determined by the particular identities, if any, amongst the relative properties on Donnelly's view. And we can identify what that symmetry group is on her view by observing how the relation behaves in its range of applicability to a given set of objects of an appropriate number. We can observe the behavior by observing the behavior of so-called order-determined predicates, which express that relation. And an order-determined predicate is just a predicate such that the implications of any relational claim involving it, and here I'm quoting Donnelly, concerning the order of relational application are completely determined in some fixed way by the order of the terms denoting the relata relative to the predicate. So playing tug of war with is not order determined because this ordering, notice that this ordering of Alice, Bob, Carol, and Diane is the same as this ordering of Alice, Bob, Carol, and Diane, but we can associate them differently on different sides of the predicate. And these, of course, are two different completions, right, of the tug of war relation. So we need to kind of find an appropriate predicate in order to make sure that we don't get ourselves confused by this feature of these infixed predicates. And we can often do that just by rendering it in first order logic and using a prefix predicate to do that, because then, you know, association on either side of an infixed predicate is no longer possible. So anyway, she defines symmetry groups as follows. For any order determined n-place predicate R standing for any n-ary relation R, the symmetry group for R, the predicate and the relation, you can think about those things as interchangeable, is the set of permutations such that for any x1 through xn, referring to objects in the domain of R, Rx1 through xn is equivalent to Rxp1 through through xpn, where you're just now permuting the terms, you know, with a given permutation. And so the symmetry group is just going to be kind of the group of all those permutations that you can do that with and have equivalent statements. And then here's the other big piece of her view that really makes the difference as far as being able to get the right numbers of completions for symmetric relations versus non-symmetric relations. The number of relative properties a relation has and how they can be instantiated by some objects relative to one another when the relation applies to them is indicated by the relation symmetry group. So the things that determine the number of ways, these things determine the number of ways an n-adic relation can apply to m objects where m is less than or equal to n according to the following principle. So let T sub q be the relative property, which when x1 through xn stand in R, in that order, xq1 instantiates, let me read that again. So let T sub q be the relative which when x1 through xn stand in R, it's the relative that xq1 instantiates relative to, oh, and there should be a q here, sorry, relative to xq2, and so on relative to xqn. So the principle is a relative property, TQ, is identical to a relative property, tau q prime, sorry, I'm saying T, I mean tau, if and only if there's some permutation in the symmetry group of the relation such that applying that permutation to Q gives you Q star, right? Where Q is in the permutation group, and tau Q is the property which star entails that xq1 has relative to xq2 relative to xqn. So this being star here, let me just back up for a second. So each relational claim is going to effectively determine, you know, a certain relative property instantiation, right? It's gonna entail a number of them, like we saw with the Goethe and Buff example, and then whether the relative properties that say Goethe and Buff, Goethe instantiates relative to Buff and Buff instantiates relative to Goethe, whether those are identical depends on whether there's a permutation in the symmetry group that you can apply to each of them to get the other. So a nice informal way of putting this that Donnelly gives is that relatives are associated with orderings of relata in such a way that distinct orderings are associated with the same relatives if and only if they can be transformed into one another by a permutation in the symmetry group of a relation. Now I know this is a lot, so I'm going to talk about examples next, and that will help hopefully clear any doubts that you have. So take the symmetry group of the predicate is next to, right? It's going to be S2. It's going to be the permutation group that consists of these two permutations, because for any x1 and x2, x1 is next to x2 is equivalent to x2 is next to x1, right? And by the base thesis, being next to is going to have between 1 and 2 relative properties. We can call them tau sub this, the permutation 1, 2, and tau sub 2, 1, when it applies to two things, that is when being next to applies to two things, one of those relative properties is instantiated by each of them relative to the other in each of the possible orderings of them. But here's kind of the key bit, because the permutation that maps 1 to 2 and 2 to 1 is in the symmetry group of is next to, and because applying it to the identity permutation, which is what these terms stand in, is the same as 2, 1, then we know by this principle I just gave on the previous slide that these two relative properties are going to be the same relative property. So doing a bunch of group theory, we basically get the result that the up to 2 relative properties that the base thesis guarantees being next to the relation has, we know that they're identical by using the group theory. And what this means is, in a particular case, like when Goethe is next to Buff, it's not going to make a difference how we think about those about Goethe and Buff instantiating that single relative property as to, they're not going to give rise to different completions when we switch them up. So think about each of these arrows as suggesting that, this one, for example, the top one, that Goethe instantiates tau 1 relative to Buff, and then Buff instantiates tau 1 relative to Goethe. You'll notice that since there's only one relative property that being next to has, these are the same completions, right? There's only a single state of affairs. There's no difference between this one over here on the left and this one over here on the right. In each case, Goethe instantiates tau 1 relative to Buff, and Buff instantiates tau 1 relative to Goethe. These are basically just two ways of depicting the same situation. But it's different in the case of loving, right? For loving, claims of this form, this should be love, sorry, another typo. This is the time I find all of them, right? So suppose this says x1 loves x2. This is not going to be equivalent to x2 loves x1, right? And that's going to mean that the symmetry group for loves is just going to be the group of permutations that consists of just the identity permutation, right? And that's going to mean that the up to 2 relative properties that are introduced by the base thesis are going to be distinct, because there's no permutation in the symmetry group of loves which when you apply it to the permutation that the terms are in this claim, gives you the permutation that the terms are in this claim. And so what you get is a picture like this. When Goethe loves Buff, you have Goethe instantiating one of the relative properties, tau 2, to Buff, but Buff is instantiating the other relative property, tau 3, to Goethe. And that's a different state of affairs than when Buff loves Goethe, right? When Buff loves Goethe, it's Buff who's instantiating tau 2 to Goethe, and it's Goethe who's instantiating tau 3 to Buff, right? And so these two states of affairs are different. And so you get this kind of difference in completions that you'd want with non-symmetric relations, but you don't get the difference in the case of symmetric relations, right? Now, I'll say a couple of things about a cyclic relation, but I don't have a lot of time, so I'm going to skip all the group theoretic details and just jump to the end. So according to Donnelly's view, because of the way that the group theory works out, being arranged clockwise in that order is going to have 2 relative properties. And if you have 3 things arranged clockwise in that order, A, B, and C, then A is going to instantiate one of them, tau 4, relative to B, relative to C. This is where these 2-place relative properties come in. B is going to instantiate tau 4 relative to C, relative to A. And C is going to instantiate tau 4 relative to A, relative to B. But then A is going to instantiate tau 5 relative to C, relative to B. and B is going to instantiate it relative to A relative to C, and C is going to instantiate it relative to B relative to A. And what this ends up meaning is that you'll note that when you look at all the possible different orderings of A, B, and C with respect to these properties, you'll note that when you cycle A, B, and C together within the quote unquote positions that are made by these kind of complexes of relations and their kind of permutation theoretic relations to one another, you'll note that when you cycle these objects with respect to one another, you don't end up changing the assignment of relative properties to them. It's just when you transpose two of them that you actually get a difference in the assignment of tau 4 and tau 5 to A, B, and C. And so what you end up getting in this case is you end up getting two completions of being arranged clockwise in that order by three objects, which is the number that you'd want, right? And it's amazing how fast time has flown. I wish I could have gotten into the details, but you can feel free to ask me about them later. So to the extent that you may have understood this stuff, just because it was so quick by necessity, I want to now generalize the standard view and see if I have any time to actually give an argument for the standard view at the expense of Donnelly's view. And I'll be quick. I won't go into the details as much because I think the transfer is actually relatively straightforward. And I think the way that I've depicted the sorts of examples in Donnelly's view has already primed you, hopefully, for knowing what's going to happen. So I just make an observation about her view, which is that on her view, each relative property is instantiated by some x1 relative to some x2, and so on relative to some xn. That is, each relative property can be understood as kind of being instantiating in a kind of by these things in a total order, right? And according to the standard view, each relation is usually taken to apply to some x1 through xn in a total order, right? And so making that observation, it becomes pretty straightforward to kind of see, well, wait, why don't we just say that the things that relative position posits as relative properties are actually just the relations? And then what we'll do is we'll interpret the application of those relations as the standard view theorist is going to interpret it. They have a direction, or alternatively, they apply to their relata in an order proceeding from one to another to the remaining one, right? And so all I've got here is just kind of a standard view theoretic version of Donnelly's base thesis, which I'm not going to go into in detail. Hopefully you kind of see roughly how it's going to go, is just that each relation is going to have between 1 and n factorial minus 1 converses. That gets McBride's 5 converses for a completely non-symmetric ternary relation. And then, each of the converses is going to apply in some ordering of them, and every ordering is going to be such that at least one of R and its converses applies to them in that order. So Loving's going to have between 1 and 2 converses just by the base thesis. Being between is also going to have just between 1 and 2 converses, but it's going to be the group theory that again tells us that in the case of being next to, it's going to be its own converse, right? And in the case of, and so we're going to get identical completions when you kind of switch them around, because there's no difference for Goethe standing and being next to, sorry, that's the way I want it. There's no difference between assigning Goethe and Buff in this way or in this way. These are just two different pictorial representations of the same state of affairs. Now compare that to the case of Loving, right? Because of the group theory and the way that the predicate loves works, Loving is going to have one converse and it's going to be distinct from it, namely being loved by, right? And so when you switch Goethe and Buff in the quote unquote positions that result from this kind of complex of relations, you get distinct completions, right? Now, in the case of the ternary relation I talked about before, things are going to work out exactly the same. We're just now interpreting these arrows as relations rather than as relative properties. But again, you get two completions because cycling A, B, and C around in these quote unquote positions doesn't result in a different assignment of relations to them, but transposing any two of them does, right? So I will grant that the standard view is going to be a bit revisionary because it's not like you have a single relation being arranged clockwise in that order, which is expressed by this predicate. Instead, and I'm taking a play from Donnelly here, I think that these relations in the case of this predicate are best understood as R4, for example, is best understood as saying that R4 is the red one. So let's follow this red relation right here that bounces around across B. R4 is understood as being clockwise in front of from the perspective of. So let's read this one. A is clockwise in front of B from the perspective of C. And when you imagine yourself in C's perspective, you'll notice that kind of as you go around the circle clockwise, you'll hit A first before you hit B, right? And that's why R4 applies to A, B, and C in that order, right? And not R5, which is to be interpreted as being clockwise behind from the perspective of. And we have to modify SV2 and SV3 a little bit more just to accommodate relations of arities larger than binary. Because as it happens, well, one thing that happens in the case of some say ternary relations, not the being arranged clockwise one, but like say being between, it's going to have two converses distinct from itself. And so you can't really, it doesn't really make a lot of sense to say that that the direction the converse of the between relation applies in is opposite its own. But we can say that it's different from its own, right? And I think that's enough. It's just a kind of a non-identity permutation. So in the case of being between, what we have is we have three relations. And if you'll notice that in this case, if you transpose B and C, you don't get a different assignment of relations to the relata. It's only if you transpose A and C or A and B that you actually get a difference. And some kind of the most straightforward interpretations of these relations for this, for the red, well, let's start with the black relation, just because it's most prominent. Being behind from the perspective of, you'll notice that from this perspective of C, B is behind A, right? Kind of has to look over A to see B, right? And this is the one that kind of is kind of egalitarian in the way that it applies to A in a way, right? The idea is that it's only if you kind of trade A out for C or B out for, or A out for B that you kind of get a difference in completions. So the second thing that we have to do is we have to kind of distinguish between a complete symmetry, complete non-symmetry, and partial symmetry, because these relations that I've talked about, like the cyclic relation being arranged clockwise in that order, and the between relation, they kind of have partial symmetry, right? You can perform certain permutations on the relata without resulting in a different completion, but you can't perform any arbitrary permutation without doing so. And so we would just change SV3 to say that, you know, a completely symmetric relation is its own only converse. A completely non-symmetric relation is going to be distinct from each of its converses. And then a partially symmetric relation is going to be distinct from at least one of its converses, but it's also going to be a converse of itself, for the basic reason that any partially symmetric relation, if it applies to x1, x2, and x3 in that order, then it is also going to apply to them in some non-identity permutation of x1, x2, and x3. And that's just a fact about partially symmetric relations. All right, so that being said, let me try to talk about an advantage of my view over Donnelly's. And it's just that Donnelly's view, I think, has to posit relative properties in all cases of relativity, whereas the standard view, just being a view about relations, doesn't. So what's relativity? It's just the phenomenon where a property or relation is instantiated only relative to some other object or objects. So an example, potential examples might be that something's north only relative to a location, or something is bent only relative to a time. And Spencer, in his 2016 paper, talks about two ways of dealing with relativity. The first is what he calls relationalism. And the idea is that, we might be tempted to capture all cases of relativity with relative properties, but the relationalist will say, well, a putative n-ary relative property or relation is actually an n plus k-ary non-relative relation, where k is the number of arguments which the property or relation was originally thought to be instantiated relative to. And I'll go through an example in a second. Variablism is the idea that a putative n-ary relative property or relation is genuinely n-ary, and its relativity is captured by the fact that its extension can differ when the value of a parameter associated with that property or relation or an index differ. So an example, say north, right? Something is north only relative to a location. The relationalist is going to understand this as kind of being underwritten by a relation, right? It's not being north isn't a unary property, but it's instead a binary relation, which takes a location as its second argument. So they're going to think about the extension of, well, they're going to think about being north as a binary relation, and they're going to think about its extension as just a set of ordered pairs, right? But the variablist, they're going to treat being north as a genuine unary property, and it's just going to have a location parameter, which when it takes different values, changes the extension, or at least can change the extension of the property. So on this view, the extension of the property being north is going to consist of these ordered singles when the parameter is LAX, when the location parameter is LAX. But it's just going to consist of Seattle when the location parameter is Portland, right? And so this is just two different ways of thinking about cases of relativity. One is think about it in terms of a relation, but another is to think about it in terms of a property, right? With this kind of variable parameter. Another example being bent. Something is bent only relative to a time. The relationalist will say, well, this isn't a unary property, it's a relation, binary relation, which takes the time as its second argument. So the extension of being bent is going to look like this. It's going to have, in it the pair Lewis and T1, and it's going to have in it the pair Thompson and T2. Variablism, on the other hand, is going to think of being bent as a property. When you fix its time parameter at T1, it's going to contain Lewis. And when you change its time parameter at T2, it's going to be Thompson and maybe some other people in each of those cases. So there really is a substantive difference, I think, between non-relative properties and relations and relative properties and relations. And the idea is that behind Spencer's paper is that non-relative properties and relations should be given a relationalist treatment, and relative properties and relations should be given a variablist treatment. Non-relative properties and relations extensions intuitively aren't going to vary. Relative properties and extensions vary across parameters, which can take different values. So in this way, non-relative properties and relations and relative properties and relations are going to be different. And then the instantiation relation that non-relative properties and relations stand in to their relata is going to be presumably non-relative. SFO and LAX instantiate being north in that order. And then SFO is going to instantiate, oh yeah, well, let me back up. As far as the instantiation relation that relative properties and relations stand in, it could be either non-relative or relative. And part of Spencer's project is to argue that it should be understood to be relative. But either way, there's a substantive difference between non-relative properties and relations and relative properties and relations. Because under the assumption that the instantiation relation they stand in is non-relative, then the instantiation relation that n objects stand into an n-ary non-relative property or relation is n plus 1 ary. and the instantiation relation that n objects stand into an n-ary relation, relative property or relation is n plus 1 plus k-ary, where k is going to be the number of parameters of that relative property or relation, right? And then, of course, if the instantiation relation that relative properties stand into their relata is relative, then the instantiation relation that non-relative properties and relations are going to stand in is going to be non-relative, and the one that relative properties and relations are going to stand in is going to be relative. So there's going to be a substantive difference between relative and non-relative properties and relations either way. And Spencer talks about a couple of tests to kind of reveal the difference and to show us in a given case of relativity when we should be understanding it in terms of relative properties and when we should be understanding it in terms of genuine relations. And because I'm low on time, I'll just talk about one of those tests, the one I think is the easier to get your mind around, the switch the index tests. So Spencer tells us to consider a putative n-ary relative property or relation R with a presumptive parameter P. Like, well, I'll give examples in a second. Suppose x1 through xn instantiate R relative to index I. Now swap out R with a putative n-ary relative property or relation whose instantiation by the n objects relative to I would result in a completion incompatible with the first, but change I to a new acceptable value j. If intuitively x1 through xn have undergone a change, then R is a genuine n-ary relative property or relation. And if not, it's an n plus 1-ary non-relative relation. So in the case of the endurantist's time relative shape properties, we say being straight is instantiated by Lewis relative to T1. Now do the thing the switch the index test tells you to do. Switch being straight out with a, kind of an incompatible relation, right? That if everything stood in it, if Lewis stood in it relative to T1, it would create a completion incompatible with the first one. Being bent is instantiated by Lewis. Now switch out the index to a new index relative to T2. Intuitively, Lewis has undergone a change. So being straight is going to be a genuine relative property on this view. But now think about size. Being big is instantiated by Remy. This is Spencer's example, relative to mice. Being small is instantiated by Remy relative to animals. It's not the case that intuitively Remy has undergone a change through this process. So being big is a binary non-relative relation. You can think about it as a relation to a comparison class, right? And that's how we should think about it, according to Spencer, given the switch the index tests. So just to talk about being adjacent and just a couple of the examples we've talked about. Being adjacent is instantiated, we can suppose, by Goethe relative to Buff. Being distant is instantiated by Goethe relative to George Washington. It's not the case that intuitively Goethe has undergone a change, so it would seem by this test that being adjacent is a binary non-relative relation, being next to, as we've supposed. Similarly with being a lover, right? Being a lover is instantiated by Goethe relative to Buff. Being a hater is instantiated by Goethe relative to Carolyn Herschel. It's not the case that intuitively Goethe has undergone a change, so being a lover is a binary non-relative relation. Now, my basic point here, and I have this other test, but I'm not going to talk about it just because I'm getting past time here. But I just want to say that according to Spencer's view, sometimes it's appropriate to understand relativity in terms of genuine relative properties and relations, but other times it's not. And the disadvantage of relative positionalism, I take it, is that in every case, Donnelly is forced to understand relativity in terms of relative properties. But the standard view is totally compatible with just taking the cases of relativity that we think should be dealt with relations and saying, my account applies to those only. I'm not saying anything about how other cases of relativity should be understood. I'm not saying anything about what it is for a relative property to be instantiated. I'm just talking about relations. And so that, I think, is kind of the main difference between the two views. I've tried going a bunch of different ways, and I think that this is, so far, the strongest case I've settled on. So hopefully, to some extent, at least in the short time I've had, I've given you some idea of how the standard view can be adapted to dealing with any fixed-arity relation with any symmetry using Donnelly's techniques, and hopefully giving you some idea of why we might prefer the standard view, at least to relative positionalism. So I'll stop there.